Hello, class. I thought that I would start the next lecture. I was sort of thinking about how I was going to go through this, if I was going to continue with the derivations dealing with the capacitors, or if I was just going to go into a physical fundamental understanding of the difference between capacitors and inductors. And I think I'm going to start with that. So if we go back to that original circuit that I showed you in the beginning, we had that switch, and then I had a resistor and I had a capacitor, and what we realized was that as soon as I throw that switch, so at t equals 0 plus, we are going to see it starts as a short circuit, right? So it starts short circuit, ends open circuit, right? So let's just box that in, because we've spent a lot of time talking about the fundamentals of a capacitor in a circuit and what it starts at, right? So as soon as the switch closes, this thing looks like a short circuit. It looks like it's not even there. It looks like it's just a piece of wire like this, right? But then after a period of time, the current is going to go from a maximum to a minimum. In fact, if we were looking at the current, let's put our power supply in there. If we were looking at the current, we see that the current is a maximum, right? So if we look at capacitors, we've got two different types of graphs here. Both of these are time on that scale. And then if we're looking at voltage across the capacitor, right? So here's my voltage across the capacitor, right? So if we're looking at the voltage across the capacitor, in the beginning, it's going to start at 0, right? It's going to start at 0, and then it's going to pile up, eventually getting to a point where it asymptotes off at 50 volts. Didn't we say that was 50 volts in the last one? I can't remember what we made this. I think that was 100 ohms, wasn't it? If I remember correctly. So if we were to look at the actual current flow, it's voltage divided by, no, didn't we get 0.5 or something like that? Voltage divided by, what did I make that? Just a second. I'm going to pull this. I'm just going to see what I made that. Someplace around there. 100 ohms. No, I didn't. So yeah, 50 divided by 100. Yeah. So 50 divided by 100 ohms is going to give me 0.5 amps. So my current is going to start at 0.5 amps, right? That's what we figured out. And then it's going to go down eventually to 0, right? Because it starts at us as a short circuit and it ends as an open circuit. Now you're probably saying, God, he has like beaten that theory to death, hasn't he? I mean, I will remember that a capacitor starts as a short circuit, ends as an open circuit, that there is no current that actually is flowing across the capacitor whatsoever for the rest of my life. And that's what I want you to remember. That's what I want you to remember. Here's another thing I want you to remember. Let's look at that same circuit, but instead, I've still got my 50 volt power supply. I've still got my switch, but now, and I've still got my resistor that's a 100 ohm resistor, but now I'm going to put it through an inductor, right? Oh God, this, give me that. And you can be erased too. Yeah, there we go. All right, sorry about that. I missed the line. So I'm going to try to bring that through here and bring that across down there. And here is my my ground. And here is my 50-volt power supply. Now, I've still got my 100 ohm resistor there. The difference, though, is I have an inductor here, right? Instead of a capacitor, which we call C, we've got an inductor, which we call L. I know what you're thinking. God, if the capacitor starts as a short circuit and ends as an open circuit, does the inductor do the same thing? Does the inductor start as a short circuit and end as an open circuit? No. The inductor starts as an open circuit and it ends as a short circuit. Okay, let's look at a couple graphs of that. Again, these are time, right down on the x-axis is just time. But what does, and you're probably thinking, well, they're going to be just exactly the opposite, right? They're going to be exactly the opposite to my capacitor things. In fact, the voltage across a capacitor is 0 because it starts as a short circuit. But you know, the voltage across the inductor, right, is going to start at the 50 volts. And it is going to slowly, right, become a short circuit, so it goes to 0 over a period of time. How about my current? Right, there's my voltage across the inductor. That would, of course, be the same thing. There's plus, minus. What's my voltage? If I put a probe here off a digital multimeter and I put a probe here off my digital multimeter, what am I going to get, right? So that's what the voltage across there is. What is the current through the inductor? Well, it starts as an open circuit, right? So if it's an open circuit, there's not going to be any current flowing through there. And then what happens is it eventually gets up to a maximum. And what is that maximum? 0.5 amps. So you can see that the two graphs of voltage per unit time and current per unit time are exactly the opposite for an inductor as they are for, right, voltage goes up like that, voltage goes down like this, current goes down like this, current goes up like this. So that's what you've got to realize. Now, I want to talk about the actual mechanism that's occurring. Why does that? Remember, I talked before about this is really setting up an electric field. There is no current that flows across a capacitor. It's setting up an electric field, and as it sets up an electric field by causing electrons to flow to one side of the capacitor and an electron holes or positive charge or whatever you want to call it, the lack of electrons to flow to the other side, we set up an electric field through the dielectric, and that, of course, polarizes the dielectric, and eventually it becomes a open circuit. When we can't pump any more electrons into one side and take any more electrons off from the other side. So the electric fields become static, and then, of course, just like I said, it goes to an open circuit. What's going on with a inductor? And to explain that, I want to draw a line. Now, you don't know this yet. You're going to know it when you take motors and controls or whatever your magnetic field course is. Usually it's motors and controls. If I have a current that's flowing through a wire, right? Take your thumb and put your thumb in the direction, right? Your thumb is in the direction of current flow. Now, let's say that I'm actually looking at the end of this wire, right? So this is me looking at the end of the wire. In fact, we have a convention. If we're looking at the end of the wire and the current is coming toward us, it's that. Current toward us is that. It's the tip of an arrow. If I was to look at this, it would be the tip of an arrow. I suppose I could draw it sideways. It looks like this, right? There's my arrow, and the tip is painted black. So it looks like a tip of an arrow, and it implies that the current is coming toward you. How about if the current is going away from you? If the current is going away from you, we see the arrows on the back of an arrow of the current, right? So if the current is flowing away from me, it's the arrows. Like this would have arrows on the end of it. So that is current away from us. All right. So let's look at that, and let's look at, we used our thumb to go in the direction of the current flow, right? And so if our thumb is going in the direction of the current flow, our fingers describe, with this being the tip of the arrow and this being the arrow, the arrows on the arrow. This is the tip, that's the arrow, right? Do you see how the magnetic field? Let's put it here, right? Isn't that coming out of the board? So wouldn't my magnetic field lines be going around this way? Does everybody see that? Did your fingers all go around that way when you stuck your thumb up? Yep, my fingers go around that way. So I've got a magnetic field that is created by the right-hand rule around my wire, and I'll just try to draw this. Right, it goes around like that, just like I've drawn here. Right, so there's it's hard to draw in 3 dimensions in a 2-dimensional plane, but I think everybody can see what I'm talking about. Is if the wire is coming, it's going around like that. Now, let's take that a little bit further, because we haven't quite created our inductor, have we? So what I'm going to do is I'm going to take this wire, and I'm going to twirl it around, right? So that it keeps going down like that in some type of a spiral. Now, my current is still flowing through there, isn't it? I'm just going to draw some things here, right? My current is still flowing through there, so that if I did have, let's say I put it on some type of thing that I could wind it on, maybe a piece of plastic or whatever, or a piece of ceramic, and I had the wire coming in like this. I'll try and draw it better in 2 dimensions than I did in 3 dimensions. And I've got wire wrapped around there, right? And my current is still flowing through there. In fact, everybody, I think, can see that if it goes like that, then it's going to come out the other end. So I've got my current flowing around there. Let's look at this then from the top. Right, let's do another look down into the bottom there, and then I'm going to put the thing that I'm wrapping it around right there, and then I'm going to put my wire that I've wrapped around that, right? And as you can see, if I'm looking down here, look at the thing. My wire is going back here, and then my wire is going around, and it just keeps going down and down and down, right? Until finally it's going to come out the end there. Well, which way is my current going? My current is going this way, isn't it? And I've got wraps and wraps and wraps of turns around there. And then my current finally at the very bottom comes out this way. You know, if we take our right hand and we lay it around here, right? then I think everybody can see that the lines are coming from the bottom up to the top. There's an easier way to do that, though, and I'm just going to teach you this trick. I don't know if all of your professors later on are going to know this, but eventually you can see. I think it's very obvious, and this is the way I learned it, and it's the way that I think most of your professors will probably teach it to you too, is that if you take your thumb around there, then it looks like the lines of force are coming up and then they're going on the inside and then going down, right? So they would be coming like this. Can everybody see that? Right, so my lines of magnetic force are going to be going like this. And then, of course, I would have parallel ones that are coming up here. And you're probably saying, God, I can't see how that goes. I'm laying my thumb there. I can't, yeah, I had friends that couldn't do it. I'm laying my thumb here. I can't see how, those are going to go inside or whatever. Here's an easier way. Here's an easier way. Take your fingers, right? Take your fingers, because you're going to learn about this in motors and controls, and this is really going to help you in motors and controls. Take your fingers and lay them in the direction that the wrapping is going, that the current is going, right? The wrapping is just wrapped around, but the current's flowing through this way, right? Because it's flowing in behind it, then it's flowing all the way, and then it flows out, right? So we know the current's going this way. So which way is your thumb pointing? That's right. Your thumb is pointing down. So your flux lines are coming out of the bottom. They're called flux lines, yes. They're coming out of the bottom and they're going up to the top. Now you're probably thinking, God, that's a magnetic field. That's right. He's wrapped it around a torus. So I've got a magnetic field that goes this way around the wire. If I lay my thumb in that direction, I know that the current is going to create a magnetic field in concentric circles around the wire. Wire's coming out, it's going that way, right? And then if I was to wind it around something, let's say a piece of ceramic, how about if you wrapped it around a cardboard toilet roll holder? Right? You could make an inductor like that, couldn't you? It'd be an air core inductor. But let's say that's like a toilet roll and you have wrapped wire around it. When I was about 11 years old, I actually did that, and my dad helped me make what was called a foxhole radio that they used in World War II with a safety razor. There was no crystal or anything. It's just a safety razor. I could go into that, but we've got so many other things to do. So anyway, this is here. Now, where's the North Pole? Where's the South Pole? That's a good question. We know on every magnet that the flux lines leave at the North Pole and they go back in at the South Pole. Does everyone see that? Get these concepts, these physics, these fundamental physics concepts that you're going to need to understand things for when you do motors and controls. And there's many other applications for magnetism besides the inductor, right? Now I want to point something else out that's interesting about an inductor. Well, first of all, the wire goes all the way, doesn't it? Now, why does it start as an open circuit and why does it end as a short circuit? Why does it start as an open circuit? Why does it end as a short circuit? All right, I'll tell you. The inductor has three names, right? Inductor, it's got another name we also call an inductor, and you'll hear this referred to, especially by older engineers a lot, as a coil. Why do we call it a coil? Well, because it's all coiled up, isn't it? That's what it looks like. It looks like a coil. So sometimes it's called a coil. But it also is called a choke. Why is it called a choke? Because when current first starts flowing into the inductor, when current first starts flowing into the inductor, the inductor chokes back the current. Isn't that what happens here? Isn't the inductor choking back the current? Because what is that current trying to do? The current is trying to create this huge magnetic field, right? So the first current that goes in here is slowed down as the magnetic field is growing. The current that's coming in is really going into growing this magnetic field. So this magnetic field, as it grows, is choking back the current. It's a current choke, isn't it? Why do I write these things so large? It's a current choke. That's why we call it a choke, because when it first starts, it starts choking the current. Now, this doesn't really come into play so much in DC as much as it does with AC. As much as it does with AC. I'm not going to get into that. That's for network theory too. And but that's why it's called a choke, because it's a current choke. It chokes things off. It doesn't start as a short circuit. It starts as an open circuit. So there's no current flowing through. When I draw this circuit right here, what happens is the current wants to go, right? Immediately when I throw that switch, that current wants to go, and the current flows all the way to here. When it gets there, it's choked back by the inductor, because the inductor, which doesn't have a magnetic field already, is creating its magnetic field. As the current first starts to flow through, it's creating this giant magnetic field that it's going to have at the end, isn't it? So all of this current is choked back until, you know, the magnetic field is entirely done, and then the current will continue flowing on, right? So that's what you've got. You've got something that is a current choke. Starts off as a current choke. Now, if I had an open circuit there would be no current flowing, right? But some applications require current to start slowly, but then to get up to a maximum later on, right? Okay. Have I even turned that? I have turned it on. Okay. You know, it takes a lot longer to explain the physical science behind, and a lot of other things that we've learned here about magnetic fields, you know, current flowing through a magnetic field. That's going to come back in, to haunt you in transformers, isn't it? It's going to come back to haunt you in relays. It's going to come back to haunt you in motors and generators, right? I'd love to teach that course, but I can't teach everything. So let's get back to this. Now, what I want to do is I want to go back, now that we've discussed the physics underpinning inductors, what I want to do is I want to go back for a second to capacitors. And I want to talk about capacitors and the mathematics that go into capacitors too. I'm not going to derive everything, because this isn't a course on electromagnetic field theory and electrostatics and stuff like that. I teach that to you when you're seniors. If you're in the electrical engineering course, you'll have a fantastic, you know, if you want to learn about electromagnetic field theory and you happen not to be in the electrical engineers, you can look at my course on the Scott Grenquist YouTube channel on electromagnetic field theory. It's right up there, and you'll learn everything about electrostatics and electromagnetic field theory you ever wanted to learn. As an introductory course, is about 1.5 course. All right, now let's get back to this. I said before that Q equals C times V. Charge equals capacitance times voltage, right? You know, what if I took Q? Where have we seen that before? That's charge. You know, isn't an amp equal to a Coulomb per second? Wouldn't that make a Coulomb equal to an amp second, right? Does everybody see that? So a Coulomb is an amp second, or it's current times time. Current times the change in time gives us the change in C, right? Wouldn't that be, or charge? So let's call, I probably should, since I'm using Q there, let's use Q over here. Then I won't get you too confused. I use coulombs, and I'm using the numbers, but in fact, then what I should do is I should use an I here, shouldn't I? And instead of S, I should probably use dt. Look at that. So I equals Q over dt. You know what? I bet that I equals the change in charge over the change in time. I equals dq dt. Isn't that right? Wouldn't that be the change in coulombs over seconds? And isn't I in amps? That's right. So we've got a couple relationships now, don't we? We know that I equals dq over dt. We know that Q equals C times V, right? I'm going to give you another one that I'm not going to actually derive this, but I want you to remember this. I derive it in electromagnetic field theory, so if you want to go and look at capacitors and electric fields and electromagnetic field theory, I think it's about the 36th lecture. I look at that. But I'm going, or I derive this equation. So this is epsilon A divided by D. That's how I find the capacitance of a capacitor. Now let me just draw a capacitor and just explain what these individual variables are, right? So let's say I've got my capacitor here, 2 plates separated by a dielectric. I'm going to get the green pen to, I've got a nice dielectric insulator. Not all dielectrics are pure insulators, but most are. All right, so I've got a voltage across here, right? My dielectric has a permittivity. That's right, that's what that is. I'm going to tell you. This equals permittivity. And I'm going to let you know some things that your book isn't telling you. The permittivity is really the same for everything. If I look at the permittivity, if I wanted to look at permittivity for any material, it's the relative permittivity times the absolute permittivity. Everything is related to the permittivity of outer space. We use a ratio, so epsilon sub r equals a ratio. That's right. It's just a ratio. Has no units whatsoever. But epsilon sub O does. That's the permittivity of outer space. And the permittivity of outer space is 8.85 times 10 to the minus 7. Oh, wait, no, 12. I'm getting my two constants mixed up. I'm going to give you both of the constants right now. Yeah, I don't know why I put 7 there, because this is minus 12 farads per meter. So that's a minus 12. Right? I don't know. So 8.85 times 10 to the minus 12 farads per meter. And that is my relative permittivity. Why do you want to know that? Because, back, in fact, it would be in this class that you would be taught something about the the Coulombic force, the force between two electrons, repulsive force between two electrons, right? So you probably learned that the Coulombic force is Coulomb's constant times Q1 times Q2 divided by the distance between them squared. Now you're probably saying, God, he doesn't even know that. And that's right, because that's not the equation. That's what we teach Network Theory 1 students. That's what other Network Theory 1 students are learning right now is, yeah, that's a constant there, right? That's what they're learning. And it's 9 times 10 to the 9. It's Coulomb's constant. And in fact, by the very implication that we're saying it's a constant, we're telling students that, yeah, the attractive force is the same everywhere, Coulomb's constant, right? And that Coulomb's constant can't change because it's a constant. That's not the equation at all. That is not the true equation at all. That's what we do, and we dumb it down. We dumb it down for high school students. You know, we write this because we also have another equation, don't we? The gravitational equation, where I've got G times M divided by R squared. I think I've already given you a short lecture on this anyway, right? And then we tell you that, oh yeah, that's Newton's constant. That's Coulomb's constant. They're not. That is not the equation. The gravitational constant of the universe is not the same. There's a gravitational constant is not the same all over and neither is Coulomb's constant, because really this right here, this relationship is Q1 times Q2 divided by 4 pi epsilon. Now, when I say epsilon, I mean epsilon r times epsilon sub O, right? Anytime you see just epsilon, it's epsilon sub r times epsilon sub O. Now, I'll tell you the relative permittivity for air is 1.0004. So pretty much air and outer space, same permittivity, right? A lot of things have the same permittivity, but we do have certain materials that have high relative permittivity. High relative permittivity. Those allow much larger electric fields to exist in smaller spaces, right? Look at when we're making a capacitor. Is epsilon in the denominator or is it in the numerator? It's in the numerator, isn't it? So if I can get a dielectric, if I could get a dielectric to have a very high permittivity, it's going to make a larger capacitor in a smaller space. I could still have the cross-sectional area, right, still be the same. I could have the distance between these two plates, right, still be the same. But all I have to do is change E, and I'm going to increase the capacitance. If I change the material, I can increase the capacitance of that capacitor. Now let's look at a couple. Well, for mica, the relative permittivity is 5. It's a ratio. There's no units. When I look at glass, its relative permittivity is 3. When I look at the relative permittivity for barium, strontium, titanate, it's 7,500. That's pretty good, isn't it? Have you ever seen those small little circular capacitors? Those small little circular capacitors have barium, strontium, titanate as the dielectric in them. So not all insulators are the same. Mica is an insulator, glass is an insulator, barium, strontium, titanate is an insulator, but they're not all as good to make capacitors out of, are they? See what I mean? Do you see what I mean? A lot of revelations should be occurring throughout this lecture. Oh my God, and whenever I talk about concepts, time flies by, but I want to get back to this. So you see how I've designed this and the relative permittivity and the relative permittivity of all of the other things, right? And that's my capacitor. But let's get back to these. So I've got Q equals CV, and I've got I equals dQ dt, right? I equals dQ dt. So let's expand on that. I equals dQ dt. Well, what is Q? Isn't Q CV? Isn't that the same as the derivative of C times V divided by T? You know, isn't the capacitor a constant? I mean, we're talking about the capacitance of the capacitor, right? So that's going to be a constant. That can come out of there. And so I get I equals C times dV dt, right? Let's actually, that is the relationship. So as the voltage is changing, that's not going to really become important right now because we're talking about DC stuff here. So we're not worried so much about the voltage changing. But in AC, in network theory 2 that you're going to go into, that voltage is going to be changing with time, isn't it? It's going to be sinusoidally changing with time. So that means that you're going to have to remember all of the derivatives of all of the sinusoidal functions. So get busy doing that. Remember that. Okay, so I equals C dV dt. So what is power going to be? Well, if that equals I and V equals V, then I know I can just substitute that into my power equation. So power equals VI, right? Power equals VI, so that's going to be V times C dV dt, right? Or CV, well, I can simplify it. I'm just going to go CV dV dt. Pretty, might make that a little larger so it looks good. All right, now we also know that power equals energy per unit time, doesn't it? Well, if this equals this, is there anything that we could get rid of there? You know, if this equals this, power equals energy per unit time, then wouldn't power times dt equal energy? Right? Does everyone see that? So I really have, if I, let's just write this out, equals P. So P dt equals energy, doesn't it? Well, if P dt equals energy, then CV dV dt times dt must also equal energy, shouldn't it? So dt's cancel out. The C is a constant. So let's integrate that. And when I integrate this, because I've got dV, it has to be integrated, right? And that really should be E. No, that's fine, E. And then I'm going to pull C out of there. And then what is V dV? Let's just do the integral V dV, right? I think everybody can see that once C comes out of there, V dV is just going to be V squared over 2. That's right. The energy in a capacitor is equal to 1/2, that I can store in a capacitor, is equal to 1/2 the capacitance, try to make that better, capacitance times the voltage squared. Okay? All right, I've taken a little more time than usual. I'm going to talk about inductors and about things with dealing with those in the next lecture. Similar to what we've done here with the capacitor, we're going to now talk about the inductor that way. All right, see you at the next lecture.